All right, good morning. We're starting the second half of the conference now officially. This is halftime. Pace yourself. I think I'm doing this wrong, but a few quick announcements before we start with the first lecture. First, a conference key card was found in the cafeteria of the dorms. So if you have lost yours, they have it. Okay? Second, the voting booth is open in case you need to leave early. Probably the majority will do this tomorrow after the poster session. Other than that, I think I'd like to welcome David Beratan, and he's going to tell us a story about biological electron transfer. We had in the past 2 times lectures by John Goldbeck and Les Dutton. I'm blanking the name, I'm sorry. It is way too early for me. And it's a pleasure to have you here, David, and we look forward to your talk.
Okay, thank you very much, Karsten. I want to really thank you for putting together this fabulous week. I hope the students appreciate what an extraordinary opportunity this is, and I'm delighted to be part of it. So I'd like to tell you a little bit about electron transfer theory, and I think it's fair to say that the Marcus theory of the last century, taken together with the Mitchell hypothesis, really opens the book on molecular bioenergetics, really lets us think about energy flow in biology at the atomic and molecular scale, and it's really quite phenomenal. This is the 60th birthday of the Marcus theory, and we'll talk a little bit about that today. But the introductory remark I'd like to make and motivate the title of my talk is the following. If you look at the Marcus theory, what Marcus figured out so beautifully is that non-equilibrium fluctuations in the polarization of the surroundings around the donor and acceptor cofactors define the reaction coordinate and the activation free energies for electron transfer processes. And if you study his papers very carefully, although you'll see electrons in the title, you'll have to look very carefully to see traces of the electronic motion, the quantum mechanics of the electron explicitly in his theory. Of course it's there, but it's buried in a factor which many of you know called kappa, the electron transmission factor. And all of the richness of chemistry, all of the richness of protein structure and function is encoded in that kappa factor. And I believe it's fair to say that over the last 30 years that a community of researchers has been interested in unpacking that electron transmission factor and developing the structure-function relationships to explore how a protein's three-dimensional structure and its fluctuations as well influence the propensity for an electron to move anywhere from across a van der Waals contact to 35 angstroms across a membrane in a step or multiple steps. So the title of my talk then is Biological Electron Transfer from the Electron's Perspective. So I'm going to talk a little bit less probably than in prior years about the Marcus theory and the reaction coordinate, and more about the electron tunneling step and how the protein structure in electron transfer systems influences those electron tunneling steps. All right, so preface. So since I have 90 minutes, I thought I could indulge in a little bit of philosophical preface here. So I take some quotes. There's been long interest, of course, in the role for quantum mechanics in biology. And since we're discussing electrons, these very light particles that have intrinsically a wave-particle dual nature, there's been speculation going back decades on the role of quantum mechanics associated with this motion. So Longet Higgins, a pioneer in theoretical chemistry and later in theoretical neurobiology, said in the 1960s, don't worry so much about quantum mechanics. It may not be fruitful to start with quantum arguments. Start simpler. Okay. Stu Kaufman, in recent years, has come to understand the role of tunneling in bioenergetics and has asked whether these coherent phenomena that I'll be introducing today could play a larger role even in consciousness. So I think this is going to the other extreme of thought about quantum mechanics in biology. It would be considered not a mainstream argument about the role for quantum mechanics in biology. One of my mentors, John Hopfield, a very pragmatic guy who came to bioenergetics from a condensed matter physics perspective, says the role of quantum mechanics in biology is central but trivial, in his blunt and terse way. And what he means by this is, of course, you need quantum mechanics. You don't have chemical bonding without quantum mechanics. But once the bonds have formed, well, classical mechanics gets you most of the way there. This from the guy who made the first estimates of electron tunneling rates through proteins, in fact. So quite an interesting comment. Feynman was more pragmatic, and he said in his famous last blackboard, "What I cannot create, I do not understand." And so I think if we understand the role for quantum mechanics and electron transfer, we can design electron transfer proteins that do interesting things for us that might be bio-inspired, biomimetic. We might try to build artificial photosynthetic systems as well. I think that's the challenge for our community. Well, I mentioned the Mitchell hypothesis and its links here. So the underpinnings of bioenergetics and links to electron transfer and proton transfer are now straightforward. I have two ways of releasing free energy across a membrane. I can move charges across a potential. That's a sort of enthalpic contribution to the free energy. And I can move ions or any other species, neutral or charged, across a concentration gradient. And there's an entropic free energy component associated with those concentration gradients. And the famous 59 millivolts per pH unit, that comes from this entropic contribution to the free energy for moving charges either up or down a concentration gradient. And you can play with this Nernst equation, and knowing that the energy stored in ATP is about a third of an EV, 6 or 7 kcals per mole, you can say, well, if I have a membrane with a pH gradient of about 1 and no potential across it, how many protons do I need to make an ATP? And you'll come up with a handful of protons. Now, the pH gradient across the energy transducing membranes may not be exactly one pH unit. There may be a potential across the membranes, et cetera, but this puts you in the right ballpark. Okay? Since we all live at the macro scale, you might like to put these energies into perspective on the macro scale. So the energy of hydrolyzing one ATP molecule is enough energy to lift a dust particle about 1 angstrom. Okay, so that makes a macroscopic connection for the energy contained in ATP. All right, so the electron. So let's start at the beginning. It goes back to J.J. Thomson. Of course, the dual nature of the electron came out 20 or 30 years later with the rise of quantum mechanics almost 100 years ago. The quantum description of the chemical bond is due to Heitler in London. London is our hero at Duke. He moved to Duke in 1938. This is Mr. London sitting with Mr. Schrödinger. The amazing thing to me, and the Heitler-London paper actually sits at Duke. It was written a year after the Schrödinger equation, so it was a very rapid time of development of these theories. So we have the chemical bond in 1927. Now, biology, as I mentioned, by moving electrons and protons, has solved the energy problem. It uses a combination of photoinduced electron transfer reactions in photosynthesis, as well as ground state reactions in our oxidative phosphorylation pathways. And it's a sort of universal design. The energy fundamentally comes in from the sun. Electrons are transferred across membranes. Protons flow in response to that electrical charge across the membrane. And that pH gradient generates a free energy that I talked about and drives ATP biosynthesis through ATP synthase. Okay. So the broader themes that we'd like to explore today are how does biology manipulate this energy at the level of electrons and protons? So how does it control the flow of these particles so as to synthesize ATP at the end of the day from that photon that came in from the sun? Okay. So how do electrons move through folded, soft, wet, fluctuating matter? A very interesting fundamental question of how these electrons live in this stochastic environment that biology is. And what are the principles that underpin the motion of electrons over tens of angstroms to get across membranes? So if a typical membrane is 30 or 40, 50 angstroms across, electrons have to make their way all the way across that membrane. They tend to go in multiple steps of shorter distances, maybe from van der Waals contact distances to, as much as 20 or even 25 angstroms, but they go in multiple steps to get across those membranes. So we'll talk about those events. All right. So what's the logic of this vectorial electron transfer? It's critical that the electrons go in the right direction, otherwise they'll just produce heat. So if I take my solar photon and my electrons don't make that transit in the right direction, they'll just produce heat rather than stored energy that can be used to drive ATP synthase. So what's the logic? Okay, so the electrons are energized, for example, in photosynthesis by sunlight. They hop among cofactors that are bound to proteins, and we've been hearing about them throughout the week. They might be iron-sulfur clusters, they might be hemes, they might be chlorophylls, they might be flavins, they might be organic species like quinones as well. And these form the localization sites. Now, it's important to emphasize the role of those cofactors, right? So the charge is going to sit dominantly on those cofactors. It's not bouncing around the amino acid residues. It's localized. And so this is part of the logic of the vectorial electron transfer. I need to get the electrons across my membrane. If they're just diffusing randomly through my biomolecules, number one, energy will be dissipated, and number two, chemical damage would arise. So if we want high quantum yield from that photon to get into ATP production, I need to keep the electrons focused on cofactors and moving in the right direction on the right timescales from one side of the membrane to the other. So this is the sort of logic I mentioned. Multi-step electron transfer from donor to primary acceptor to secondary acceptor. Many cofactors in the chain, not just two. And protons flow in response to this electrical charge. And that's what finally builds up my transmembrane proton gradient that drives ATP synthase. Okay? All right. So here's a cartoon from the Schulten group that's very popular that shows the architecture of the purple bacteria photosynthetic apparatus. And so here's my photon coming in from the sun. These green disks represent transmembrane light harvesting complexes. They'll do exciton transfer to the so-called reaction center. That exciton transfer process itself is interesting and could be the subject of another introductory lecture. Those excitons get into the reaction center and create an excited state of the chlorophyll special pair. That electronic excited state then does its multi-step electron transfer that produces a hole on one side of the membrane and an electron on the other side of the membrane. An oxidized species down here, a reduced species up here. Q represents the quinone pool. The quinones are reduced and then protonated, so it's an electron-proton coupled process. Those are handed off to cytochrome BC1, which contributes to the proton gradient generation across the membrane. So it's electron gradient from photo-induced electron transfer to proton gradient coming from BC1. This proton gradient turns the wheel of ATP synthase, and out pops our ATP. And so that's the logic. And in a sense, what we'll be doing today is we'll be zooming in on the electron transfer apparatus of proteins like the reaction center or like BC1 to understand what's going on between these little colored squares. How do the electrons get from one square to another in the right direction at the right time scale? So if you zoom in on the photosynthetic reaction center, you see, as I mentioned, the cofactors embedded in the protein. And the electrons are going to move between these cofactors, hop, 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 until there's an oxidized equivalent on one side and a reduced equivalent on the other side of the protein. And if you further undress the protein, here you just see the cofactors shown. And so what you should start to think about is your junior level PChem textbook pictures of particles in a box, particles in a well. And so imagine if you sort of squint your eyes, that each of these colored cofactors on the right represents a potential well that's going to bind the electron. And the protein that wraps up these cofactors forms insulating barriers between those wells. And this is what gives rise to the localization that I mentioned. This is what keeps your electrons from straying, from damaging your proteins, from dissipating their energy and just producing heat. Okay? And so these electrons will go hop, 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 hop across the membrane. And the question for today is, what do these barriers mean? How can I assign a barrier height, a barrier width to the folded structure of a protein? And how can I estimate the rates of electron transfer through these barriers? Okay. There are other processes in biosynthesis that are absolutely fascinating, and this community knows better than any other one, that involve electron transfer, not for the sake of ATP production, but for the sake of biosynthesis. So this is a cartoon rendering of nitrogenase, and it's full of electron transfer reactions, from the small 4-iron, 4-sulfur cluster protein to the molybdenum iron cofactor containing protein in the middle here. Interesting process because it's ATP coupled. So this is a case where ATP energy is spent to catalyze electron transfer at the right times, at the right places in nitrogenase. So we could make a kind of laundry list of processes, and it could be much longer, but you'll see electron transfer reactions in biosynthesis and biocatalysis, oxidative damage and repair mechanisms in the genome. Oxidative stress and inflammation has electron transfer at its origin. Of course, cofactor synthesis, metal trafficking, redox status monitoring. These are all electron transfer coupled processes. Apoptosis involves cytochrome C, an electron transfer protein. Iron metabolism is intimately linked with malaria. There are, for every protein in our mitochondria, there are disease states associated with those proteins. A recent fascinating area that's emerged just over the last decade or so is transport over extraordinarily long length scales, from microns to centimeters, through so-called bacterial nanowires. These are appendages that can be proteinaceous in origin, or they can be lipid membrane extensions that are used by bacteria as well as other organisms to move electrons through their environment. In the case of bacteria, in some cases where they're starved of oxygen, they'll grow these appendages to deliver their terminal electron in the redox chain to inorganic minerals rather than to oxygen. So it's a trick bacteria use to carry out anaerobic respiration, and more. Okay, so how does biology push these electrons around? What are the physical principles? Of course, we'd love to understand how evolution manages the dual nature of the electron. This is a very deep, long-term challenge to us, I think, to explore. So the specific plans for today are to teach you a little bit about the dynamics of electrons. So we'll have to talk, at least in cartoon language, about two-state dynamics. So imagine I have two redox cofactors that can be oxidized or reduced. Let me just think about two of them, not the whole redox chain across my membrane, just the first two in the chain. They're governed by so-called two-state dynamics. So we'll speak about how electrons move between pairs of states. We'll talk about the fact that these redox cofactors are in wet, fluctuating environments. And this is exactly what Marcus theory is set up to deal with. The fact that the energetics fluctuates like mad in these media. And that's linked to the idea of vibronic broadening, vibronic coupling, level matching, and how we'll explore how those fluctuations interface with the electron tunneling step. And then we'll talk about two examples of electron tunneling. We'll talk about electron tunneling in proteins, where those barriers that I sketched for you are pretty high, very, very high, actually, compared to both KBT, thermal energies, as well as to the magnitude of the energy fluctuations that Professor Marcus described in the 1950s. And then we'll talk about a more recent electron transfer problem of interest, electron transfer through DNA, where the barriers are really qualitatively lower, and the barrier heights are on the scale of thermal fluctuations and polarization energy fluctuations, and will be in a different regime of electron transfer. Okay, so the first concept for today is that electron transfer is really a story about two-level electronic dynamics, and I'll use the word Rabi oscillations, which is a quantum mechanical word that tells you about motion of an electron from one place to another in a two-level quantum system. So let me unfold that a little bit. So what's a Rabi oscillation? Okay. Well, we'll come to that. You all remember the molecular orbital description of the hydrogen molecule or the hydrogen molecule ion. And so let me speak about that first. Not talk about oscillations, but just talk about stationary states. So imagine I make an H2 molecule. Forget about DNA for now. Imagine I make an H2 molecule. The effective Hamiltonian for that object looks like this. You might recall the Huckel Hamiltonian for ethylene. That would be another great example that you could think about here. So two orbitals interact. If I find the molecular orbitals associated with this little toy Hamiltonian, I'll find a bonding orbital symbolized by these two blue dots and an antibonding orbital symbolized by the blue and green dots. Okay? And they'll have a splitting with them between them that's twice this off-diagonal Hamiltonian interaction element. V is just the strength of the communication between those two orbitals. Okay? So what you might have in the back of your head is we're eventually going to generalize this discussion and imagine that these are donor-acceptor cofactors embedded in a protein. But let's start with just two simple orbitals like in H2 with this Hamiltonian. So I have a splitting, and the splitting between the bonding and antibonding orbitals is exactly twice the interaction element. In a molecule, the coupling element would be on the scale of electron volts. Okay. Now let's ask about this very same problem in the time domain. Let me imagine that I start out an electron on my left-hand orbital, call it D, and release it and let it go and ask the time-dependent Schrödinger equation what happens to that poor electron. And this is what happens. It oscillates back and forth forever. It starts out on the donor, and so at time t equals 0, cosine of 0 is 1. So the probability of being on the donor will be 1. Probability of being on the acceptor will be what? Sine squared of 0, that's 0, so nothing, no probability. And it'll oscillate sinusoidally back and forth for all time. There's a frequency for that oscillation that comes from the Schrödinger equation, and it's the inverse of what I'm calling the Rabi time. So there's a Rabi oscillation frequency or a Rabi time, and that's going to be critical. So the larger the coupling, let me go back, the larger the V or the HDA element, the faster that Rabi oscillation will be, that two-level system oscillation. You could call it a resonance oscillation. Okay? The faster that's going to be. The further apart these two orbitals are, the weaker their interaction, the slower that Rabi oscillation is going to be. Okay? And so that's going to be a critical time scale. We'll only have a few time scales to discuss today. This is one of the critical ones, the Rabi time. Stronger the interaction, the shorter the Rabi time, the higher the Rabi frequency. Okay. So let's just explore these timescales. So a chemical bond, carbon-carbon bond, is stabilized by electron volts, 4, 5, 6 electron volts, something like that. You can estimate the Rabi time by taking the strength of that interaction and the value of h bar, and going back to these equations here, right, and calculating the frequency or the inverse, the Rabi time. And so let's do it for electron volt scale energies. Electrons volt scale electrons bound by electron volts will oscillate between the centers involved in the bond on the femtosecond time scale. So that's what your electrons are doing in your carbon-carbon bonds. They're zooming back and forth at these super fast time scales. Now let's weaken the interaction. Let's imagine that I've got an electron transfer system, donor and acceptor cofactors separated by about 7 angstroms. Refer back to the previous two electron transfer lectures for arguments about the strength of those couplings. And they're tiny. They drop approximately exponentially for reasons we'll discuss. And the time scale of the Rabi oscillation will be picoseconds between cofactors separated by just a handful of angstroms. Okay? So, all right. So now recall the Marcus theory idea. We'll talk about more in a second. The idea that these donor and acceptor levels in my protein are in a fluctuating environment. They need to match in energy in order for the electron transfer event to occur. So in the case of strong interactions, that electronic motion happens really, really fast. And so I don't have to match levels very long in order to get electron transfer to occur. But in very weakly interacting systems, the Rabi time to get from donor to acceptor is just too long. The levels are going to go out of resonance, out of degeneracy, before I can move my electron. And that gives rise to so-called non-adiabatic electron transfer. And we'll explore all of these ideas in more depth graphically in a few minutes. These are the ideas. Okay, so the first key fact is that we've got to get our donor and acceptor levels together so that we can have this Rabi oscillation, this cosine omega t oscillation. When the levels match, we can get electron transfer. And so I want to show you a little Mathematica demonstration of this idea that my student Nick Polizzi wrote, and it's posted on the Dropbox site for the course. So this is written as a Mathematica CDF notebook, which you can run for free without even owning the Mathematica license. Just download the CDF player, or you can play it within Mathematica. So this figure here shows the Rabi oscillations of my electrons in a two-level system. So donor in blue, acceptor in red, and probability is oscillating as the electron's going back and forth. Let me manipulate the coupling. So if I make the coupling stronger by pulling that slider, the frequency of the oscillations increases. The electron goes back and forth, donor, acceptor, much faster. Make that coupling weaker. Sorry, make the coupling weaker. And the Rabi time becomes very leisurely. And the chance of getting the electron to transfer when the levels match gets smaller and smaller. And indeed, if that coupling gets super duper small, here we go, the electron will never leave the donor. It'll just be stuck. Okay? Let's go back to stronger couplings in this picture. And now let's move the donor and acceptor levels out of resonance, out of energy degeneracy. So in this picture, there's perfect energy matching between donor and acceptor, and the probabilities oscillate between 0 and 1. Let's mismatch them. And this will give you a deeper understanding of the arguments behind Marcus theory. The fact that if the energies don't match, no electron transfer can occur. So we've got this parameter delta, which is the energy mismatch. Let me exaggerate it. So now I've pulled my donor and acceptor out of resonance. So blue is donor. And so they're far enough out of resonance that no more than 20% of the electron ever strays onto the acceptor. And so let me exaggerate that even more. So if I pull them further and further out of resonance, the electron just is never leaving. So this is really the underpinnings of Marcus theory. If I want to get electron population from donor to acceptor, the energy levels better match. Okay? So I better be in this low degeneracy, this low energy mismatch regime out here, and then I can get my Rabi oscillations. Okay? So that's point number one. Okay, so I need energy level matching in order to get these Rabi oscillations, and that was part of the brilliance of the Marcus theory, is to make that recognition. And Marcus's insight was you got to that energy matching through non-equilibrium fluctuations of the medium polarization, solvent motion, motion of the protein medium in the case of biological systems, so-called inner sphere modes that move atoms and bonds around in the cofactors as well. Okay, that's two-level system. Okay, so encapsulating that picture of level matching, that Marcus picture, in a simple cartoon, it looks like this. I can have two cofactors with energy levels that don't match, no Rabi oscillation. Medium polarization brings those into degeneracy. I can get these Rabi oscillations and and polarization relaxation to trap the charge on the acceptor, and then relaxation to form the product state. These can even be self-exchange reactions, like an iron 2, iron 3 electron transfer reaction with no reaction-free energy at all. And because of medium polarization, those energy levels will be mismatched at equilibrium. And so I'll need a polarization fluctuation, even for self-exchange, to get these reactions, this electron transfer reaction to occur. Okay, so the second concept is that electronic dynamics with these fluctuating energy levels is really quite interesting. As I said, if one of my atoms is here in the room and the other's on the moon, the levels could match, but the electron's never going to do the transfer event, right? Because the matching will be too short on the time scale of the Rabi oscillation for the electron between the moon and this room to make that transit. So I'll show you a cartoon explanation of this adiabaticity issue. So let me take my two levels, just like in H2, and move them past one another. And I'll move them first very slowly past each other and watch the population change. And I'll move them quickly, and we'll see that the population doesn't change very well, very effectively between the two sites. So this is the so-called non-adiabatic and adiabatic transition discussion. Okay, here we go. So again, we've got our donor electron in blue and our acceptor electron in red. And the parameter that I'm going to manipulate, just in the interest of time, and you can play with this yourselves to change the starting point energies and the strength of the coupling, but I'm just going to change the speed at which those levels cross each other. So if they cross each other super slowly, the dynamics is a little bit complicated, but if you look at it approximately, you've got more or less a cosine squared function and a sine squared function for very slow, gradual crossing, slow enough so that the Rabi time can allow that electron to oscillate. Now let me speed up the level crossing. And here we're still doing the transit. There's some wiggles, but let me make it faster and faster. And what you see is that as the process becomes so-called non-adiabatic, it's a fast enough transition that the electron does not have enough of a chance to make that full transit. It may start to do some transfer from donor to acceptor, but the levels come out of resonance faster than it can make the full transit. And if I go to the extreme limit of a super-duper fast level crossing, you see the electron almost never makes its way from donor to acceptor. This is indeed the case in biological electron transfer over large distances, say 10 angstroms, 15 angstroms. The coupling is so weak and the crossing is so fast that it's a 1 in a million sort of event that the electron will find its way from donor to acceptor. This is the regime for most of biological electron transfer. Okay, so let's go back. All right, so that's the idea of adiabaticity, timescales of level crossings. We'll put a finer edge on that. We can make an estimate of that, the timescale for the levels to remain degenerate. It turns out to be on the timescale of femtoseconds. And so these transient degeneracies are very fleeting, very much fleeting. Okay, so I've moved my hands up and down to suggest energies are fluctuating. How do I represent that in less of a time-dependent picture? Well, I describe it as a sort of vibronic coupling or a level broadening. And this is the framework developed by Hopfield in the 1970s for describing electron transfer events. So I can describe electron transfer in this weak non-adiabatic regime using Fermi's golden rule, where the rate of electron transfer will look like a coupling matrix element squared times a Frank-Condon weighted density of states term. If you let me separate that in kind of a funny way, so I pull out one of these coupling matrix elements by itself and multiply it by the Frank-Condon factor, and take another one of these coupling matrix elements and divide it by h bar, well, this term on the right looks like the Rabi frequency. That's our intrinsic timescale for donor to acceptor electron motion. What's the Frank-Condon factor really? It's the probability per unit energy of the level matching, the degeneracy between donor and acceptor. So if I ask, what's the probability of matching donor and acceptor levels within a tolerance defined by the coupling matrix element, it's nothing more than the Frank-Condon factor multiplied by one of those coupling elements. It's this green term. So the Fermi's golden rule expression looks like a level matching probability, just as Marcus would have told us, times the Rabi frequency. Okay? So that's a nice way to think about Fermi's golden rule and long-range electron transfer. Okay. And so as I mentioned, when the Rabi time is long, the transit from donor to acceptor is slow compared to the time scale of degeneracy will be in this Fermi's golden rule, this non-adiabatic regimes. Now, if the donor and acceptor are jammed into each other in van der Waals contact, say, the coupling might be fast enough so that all of the level crossings will produce electron transfer, and that's the so-called adiabatic regime that was of interest to Marcus in the early days of electron transfer, of particular interest. Okay, so let's discuss this alternative view of Hopfield for interpreting the Fermi's golden rule expression in a related way. So we can take Fermi's golden rule, 2 pi over h bar squared coupling matrix element times a Frank-Condon factor, and associate the details of that Frank-Condon factor with the probability of broadening the donor and acceptor energy levels by a certain amount. And so he built a simple model analogous to Marcus's model, where the polarization fluctuations were Gaussian. And so, these energy fluctuations were Gaussian. The potentials are harmonic. And so you can use the Hopfield model to understand the energy level broadening of the donor and acceptor cofactors in a particular medium. And the absolutely critical statement to make is that these non-equilibrium polarization fluctuations broaden the electronic levels by energies of order square root of lambda reorganization energy times Boltzmann's constant times temperature. Okay? So the fact that your donor and acceptor cofactors are in a thermal medium that's fluctuating broadens their levels on the scale of square root of lambda kBT. Okay? So if these molecules, these cofactors, were sitting out in space, out in the gas phase, their levels would not be very much broadened at all. They would correspond to these horizontal red and blue bars. But because they're in the condensed phase, in this aqueous medium, they're broadened, and this is the broadening. So these energies are big. These broadening energies are big. They're in biological systems on the scale of tenths of electron volts. So fully an order of magnitude larger than thermal energies, than kBT, right? kBT is 25 millivolts. So they're fully a factor of 10 larger. So these donor and acceptor levels are fluctuating up and down all the time in our proteins. Our cofactors have energetics that are fluctuating on the scale of tenths of electron volts, just through thermal fluctuations. So this way of formulating the electron transfer theory allows you to think in terms of the cofactor energy fluctuations. And that's convenient because it lets us understand how much the donor and acceptor cofactor levels are moving around in the energy landscape of the protein. We'll talk more about that and why that matters. Okay, so we have those fluctuations. They're big. An appeal of the Hopfield framework is you can introduce nuclear tunneling in a phenomenological way through an effective temperature, but that's beyond the scope of what we want to talk about. And it's formally equivalent to Marcus theory in the high temperature regime. It's just a little more convenient. So now I'd like to, with the physical principles in hand, I'd like to start to think about models, explicit models for moving these electrons through a protein medium on the scale of angstroms to nanometers. Okay, so this is a cartoon representation of cytochrome C showing the covalent bonds and non-bonded contacts within some cutoff length. So it's a big zoo of electronic interactions. And somehow all of these interactions conspire to create a Rabi oscillation time and a coupling matrix element between the donor and acceptor that will feed into my Fermi's golden rule expression for estimating an electron transfer rate. And so the question we've been wrestling with for really 20 or 30 years is how can we understand how those specific interactions in a specific protein in a fluctuating environment give rise to an effective coupling matrix element to feed into my electron transfer rate. And really, we should already start thinking about thermally distributed coupling matrix elements and ensemble averages as well, and that will come up. Okay. So what is this coupling matrix element? We talked about the Rabi time, the two-level system oscillations, energy, and timescale oscillations. You can also think about them as being related to how rapidly the donor and acceptor localized states decay through this protein, right? So now I've got a cofactor that's binding an electron, and it's going to leak out because of quantum mechanics. So quantum mechanics tells me, different from classical mechanics, that my electron, although it's energetically forbidden, will have a tiny little tunneling tail to move through the protein to get from donor to acceptor, linked to this Rabi time. And the amount of wave function tail that leaks out is defined by the energy of this electron compared to the height of the barrier that it needs to move through. So now I'll start to ask the question, how could we represent, in the simplest possible models, how could we represent this protein medium between donor and acceptor as a square barrier? How would I parameterize a simple model like that? Okay, well, right. So the simplest models for one-dimensional electronic propagation through barriers looks like this. Again, junior level PChem, the wave function will decay exponentially through the barrier in 1D. And the rate at which it will decay depends on how tightly the electron is bound. If the well is deeper, the wave function will decay more rapidly. X is the distance of the electron from the edge of the well. M is the mass. So if I have heavier particles than an electron, tunneling probabilities will drop more rapidly. These models are a great starting point. This is 1970s level electron transfer theory. Hopfield and Jortner and others tried to make guesses for the effective barrier height for tunneling through proteins. Hopfield guessed it would be about 2 electron volts, and that's not a bad guess. It's really not a bad guess at all. Okay, but you can see those square barrier models are coarse-grained models. No difference between glycine and a phenylalanine, for example, in the model, just a flat potential. Just to give hints about how you could make tunneling models more atomistic, there are ideas going back to the 1960s from EPR, attributed to Hardin-McConnell, where he put periodic bridges between donors and acceptors, calculated coupling matrix elements. And it's a sort of bucket brigade story. If donor mixes weakly with bridge mixes weakly with acceptor, then you get a sort of product expression for the coupling matrix element between donor and acceptor mediated by this bridge. And instead of having a square barrier height, I have an orbital energy mismatch between the donor and acceptor levels and the bridge level, delta E. So I have a product expression, approximately, for the coupling element. Okay? All right, so you might ask, does this two-level Rabi picture break down when we have thousands of orbitals, as we might have for even a small, thousands of valence orbitals, as we might have for even a small protein like cytochrome C? So let me show you why the Rabi picture is still valid for multiple orbitals. So let me take 3 orbitals, like I just showed you in the PowerPoint slide, and calculate the time-dependent dynamics of an electron in a donor bridge acceptor system. Well, if the bridge is very far away in energy from donor and acceptor, I still get effective cosine squared and sine squared functions and very little population on the bridge, shown here in red. But if I pull down that bridge height, I'll start to get more and more mixing, right? I'll have a lower energy gap. If the coupling is strong, V, compared to that energy gap, I'll get mixing onto the bridge. So let me show you what happens here as I pull down the bridge. So I'll start to disrupt the two-level dynamics. So here you still see two-level-like Rabi oscillation, still almost cosine squared here, almost a sine squared, but the electron spends maybe 20% of its time, maybe 10 or 20% of its time on the bridge because this gap has decreased. And if you pull that gap down and make it of the same scale as the coupling, it just becomes a mess. And so you kill the Rabi two-level system picture, and you get very complicated quantum dynamics for the system. So as long as my protein orbitals are very, very far away compared to square root of lambda kBt, and also compared to kBt itself, then the two-level system picture is fine. And so I'll go back to that. So that's the approximate two-level Rabi type oscillation picture. And what I'd argue is in proteins, this picture is not bad. And in DNA, it fails. Okay, so we'll talk about that towards the end of the discussion. Okay, so don't be scared when you see a protein like cytochrome C and you start thinking about non-adiabatic electron transfer. You can still use, to start with, a two-level system non-adiabatic picture to describe it. And that's why the theory simple theories, these simple pictures work at all. Okay, so here's the picture. No orbitals for the bridge yet. Let me go back to the square barrier model and ask, well, how tightly is an electron bound to a porphyrin? What's the ionization potential for a typical conjugated cofactor like a porphyrin? Well, it's about 5 electron volts. So if I were going back to my square barrier models and plugged in a 5 electron volt barrier, I'd get a tunneling decay constant of about 2.2 per angstrom for the electron transfer rate. This would give me a qualitatively wrong answer for electron transfer. So these square barrier models, taken in a very, very literal sense, fail for us. But there are tricky ways we can parameterize them, and indeed Hopfield and others tried these trickier parameterizations. They recognized that the molecular orbitals of the protein were not 5 electron volts away, more like 2 electron volts away. And so they built empirical square barrier models that fit the energetics of tunneling through proteins. So neglecting the bonds altogether, the bonds of the protein between the donor and acceptor cofactors, is a disaster for building an electron transfer theory. We need to include them by hook or by crook. And so one way is don't use the 5 electron volt ionization potential of our cofactors, but recognize that there are bonding levels of the protein medium just a couple of electron volts away. And so if you want to build a square barrier model, as Hopfield did, take a 2 electron barrier approximately and estimate what the beta value would be for that kind of tunneling. Okay? So it's really crucial that those barrier heights are much bigger than kBt, so there's not equilibrium population of the charge carriers in the protein. And the barriers are also much larger than square root of lambda kBt, the non-equilibrium energy fluctuations of my donor and acceptor. So there's no chance of carrier injection. Boltzmann populations are infinitesimal. You'd have to go to distances close to 60 angstroms before you would get thermal population of those carriers in the protein, not relevant. Okay. All right, so here's our 2-level system again, our hydrogen molecule with our effective coupling. And we'd like to build on that for these bridge-mediated cases. Well, if you'd like to build an orbital language to get away from the square barrier models and make things more chemical, you might build systems like this. This looks like the McConnell model. You can solve these Schrodinger equations. And when the coupling is very weak, you get product forms. And I think I've written it, here. So if I have a chain of identical orbitals, proteins are much more complex than this. But if I have a periodic chain of orbitals from donor to acceptor, my coupling matrix element will be proportional to a product of the coupling elements divided by the orbital energy difference between the bridge orbitals, the red orbitals here, and the blue donor orbital. And so I could pull out a decay exponent that would look like the logarithm of the energy mismatch between the blue and red orbitals, delta E, and the nearest neighbor couplings V. And this is the famous McConnell expression for tunneling through a periodic chain. Okay. The orbital picture is already interesting compared to the square barrier picture. And that's because this decay parameter of V over delta E is a negative number. These interactions are bonding style interactions. These V elements are negative, yet the bridge creates a barrier, so delta E is positive. And so this quotient is a negative number. So that already informs the nature of protein-mediated electron transfer. Because the decay per unit in a chain is a negative number, there can be constructive and destructive interference. So this is an intrinsically quantum feature of electron transfer. And so depending on the details of coupling roots, they can interfere constructively or destructively, just like in the double slit experiment in physics. Okay. All right. So I put up a few comments on follies associated with discussions in electron transfer. And so you can already see the first folly that I'd like to point out, and that is there's one universal beta value. So the folks in the 1970s tried to estimate these beta values using coarse-grained methods, square barrier methods, 2eV barrier estimates, and that's great. It really gets you started. But if you want order of magnitude agreement with electron transfer kinetics measured experimentally, you probably need to do a little bit better. There's not one true beta value, and you see that already. The V's and the delta E's are chemical structure dependent. Okay? They depend on the protein fold, the cofactor energetics and symmetry, redox potentials of donor and acceptor, all of the rich chemistry. Not only that, but proteins are not one-dimensional objects. They're certainly not periodic, and they're certainly not one-dimensional. So if you solve the problem of tunneling through a three-dimensional tunneling of an electron away from a three-dimensional square well, you'll find the functional form is not exponential at all. It's got a 1 over r prefactor in its asymptotic form. So there's no reason to think that these toy models should really carry the day. Not only that, but if you're doing charge separation, as in the photosynthetic reaction center, you're making an electron-hole pair. And there's a Coulomb attraction between the electron and the hole. This is particularly important at the shorter distances in the early events. So it's not a square barrier at all, but there's a sort of Coulomb ramp that the electron and hole feel as you pull them apart. And so it's anything but a square barrier problem. To make matters worse, the reorganization energy of Marcus theory is distance dependent. It grows as a function of distance. It also has an origin in Coulomb's law. And so there are all these distance-dependent ingredients in electron transfer theory that you should be aware of, right? We all have to make approximations in dealing with such complex systems, but we should be aware of the limitations of simple models. Okay? I just put up a table from Kramer and Knaff's book on bioenergetics to show the range of redox potentials associated with biological electron transfer cofactors. It spans a range of 2 electron volts. So that energy denominator that you saw in an earlier slide would have the donor and acceptor levels that could move around by energies on the scale of 2 eV. So this factors directly into the beta value, the exponential decay factor for the tunneling. Okay, second folly. As I've kind of hinted by the distance dependence and the interconnectedness of these parameters, another folly is that I can really pull apart electron transfer rates one parameter at a time. You can do this, but it's not easy going. It's really hard, right? Biology often gives you one electron transfer rate. You may not have a family of electron transfer kinetics to probe. Your experimental knobs may be somewhat limited. So it's very tough to pull out these parameters one by one. Electron transfer rates have these 3 control knobs: the donor-acceptor coupling mediated by the protein, the Marcus reorganization energy, and the reaction-free energy, each of which is distance-dependent. Right? HDA through the tunneling barrier, reorganization energy through the Coulomb interaction between donor and acceptor, and similarly delta G. Okay? So not only that, but any single structure that we'd like to focus on masks the ensemble of geometries that are accessed. And we're dealing with parameters like HDA that has an exponential sensitivity to geometry. So small fluctuations can be a big deal for the coupling matrix element. Okay. Not only that, but if you want to get even more discouraged, there's no reason to think there should be a universal prefactor for the electron transfer rate. Numbers like 10 to the 13th are sensible from the standpoint of vibrational frequencies, vibrational timescales in molecules, but really the electron transfer prefactor in Fermi's golden rule also has a dependence on the donor-acceptor interaction at contact. That will be very, very much dependent on the nature of the cofactors. Adiabatic rates will not have this contact coupling at all. So it's dicey to try to connect the strong coupling to the weak coupling limit. And further, and this is well documented, well understood, there are regimes of electron transfer that are not limited by the vibrational frequency, the vibrational timescale for nuclear motion, but rather by the timescale of relaxation, the timescale, if you like, of trapping charge when it arrives on the acceptor. And so experiments, electrochemical experiments from Dave Waldeck most recently have shown that as you bring donors and acceptors closer and closer together, your electron transfer rates can be limited not by the coupling or by this vibrational prefactor, but by the timescale of solvent relaxation. Okay? So there are many possible prefactors, so this is a tough business. Okay. Just to give you a sort of perspective on the decay of the electron tunneling times as a function of distance, Winkler and Gray have made these beautiful plots that summarize experimental measurements, and there's corresponding theory that's been done as well for electron tunneling through unsaturated bridges, through simple saturated bridges, simple hydrocarbons, through proteins, through organic aromatic glasses, through glassy water, estimated from sort of back of the envelope calculations for tunneling through vacuum. And you can see that the beta values vary quite a bit. The chemical structure dependence can give rise to many, many orders of magnitude range in electron transfer rates, just because the V's and the delta E's are different for these different families of molecules. Okay? As I mentioned as well, this is a quantum mechanical problem, like the double-slit electron transmission problem in physics, and the amplitudes propagating along these multiple routes in proteins interfere with each other, and this adds a richness and an interest as well. I can give you an example. So let's use our lowest order McConnell-type models to estimate electronic propagation through a benzene ring mediated by the pi orbitals and mediated by the pi star orbitals. To lowest order, I'll just follow the upper pathway and the lower pathway for getting through the benzene ring. And what you see is that for para-coupled donor and acceptor substituents, the pathway-mediated couplings add exactly coherently, add in phase, and the coupling from the upper path and the lower path give you a factor of 2 enhancement of the coupling matrix element. You could go through this exercise. It's in the posted slides. I'm assuming that the donor and acceptor levels are midway in the HOMO-LUMO gap of the benzene molecule. Do the same calculation for meta-substituted benzene, and when the donor-acceptor levels are exactly in the middle of the HOMO-LUMO gap, you'll get perfect destructive interference. So these interference effects are very interesting and rich. These are the kinds of effects that you might be able to probe in molecular junction experiments, probably less easy to study and detect in biological electron transfer systems. So if you want to carry out a regimen of quantum chemical computation of the coupling matrix elements, they would go like this. And this is the kind of calculation that we and many other groups do today. I'll talk about simpler order of magnitude estimates in a few minutes, but this is the way things go in a molecular orbital language. If you could diagonalize the Hamiltonian for your protein at a particular geometry and calculate all of its bonding and antibonding molecular orbitals, you could use second-order perturbation theory to calculate the donor-acceptor coupling interaction, and it would look like this. It would look like the donor coupling into all of these orbitals, every one of these bonding and antibonding orbitals, and that's VDB. And the coupling out from the bridge molecular orbital number n to the acceptor on the right-hand side. And each one of those coupling products in the numerator carries with it an energy penalty. It looks like first order, second order, I should say, perturbation theory. But now we're working in a basis of bridge molecular orbitals. So one way or another, this is the kind of strategy that we and many other groups use to apply quantum chemistry for calculating these couplings. And if you wanted to do it really right, you would sample geometries of your protein and do an ensemble averaged estimate of this squared coupling. Okay, and so that's just more details. Okay. All right, so these ideas of simple exponential models and decay per bond ideas will vary very much as the energetics and the symmetry of the orbitals change. There can be constructive and destructive interference among the pathways as well. And both bonding and antibonding states matter. It depends on the energetics of the donor and acceptor as to which might be dominant. Okay, so the next concept I'd like to introduce is that electron tunneling in these soft, wet, fluctuating systems can be dealt with in various ways, depending on whether the barrier is high or low. So let's drill into the protein electron transfer problem in a little more detail. Okay. So we know that our cofactors bind our electrons by about 5 electron volts. Proteins, although they're not periodic structures, are nearly, their backbones are close to being periodic with the the residues being chemically different. And we know that the cost of tunneling electrons through space is very high compared to the cost for tunneling them through bond. So there are basically two kinds of interactions at a coarse-grained level that we need to take care of in biological electron transfer. One is a through bond tunneling, and one is a through space tunneling, through space tunneling being much more costly. So how can we go beyond the square barrier models and capture this sort of dichotomy through bond, through space coupling? Okay. Well, you can bite the bullet and do quantum chemistry, and it's really tough, right? Try to harness the power of modern molecular quantum mechanics and statistical mechanics. It's tough, and it's tough for the following reasons. The system sizes at play are enormous. The cheapest calculations we might like to do that include all the valence orbitals would scale like the cube of the system size. The range of timescales, as you all know, is enormous for protein thermal fluctuation, so I need to capture the ensemble of protein geometries. If I'd like to approach this degenerate state, I might have to capture rare events that bring donor and acceptor levels into energy level matching. There's a terrible problem in most modern density functional theory associated with charge transfer itself, just getting the extent of charge transfer to be right in the calculations. We're also dealing with wave function tails, very, very tiny amplitudes. And we usually use Gaussian orbitals to do quantum chemistry. They will qualitatively misrepresent the wave function tails, so we need to build larger and larger basis sets. Very tough to describe these wave function tails. We also do variational calculations, which are aimed at calculating energetics. Well, wave function tails are very tiny. They make very little contribution to the energetics of the cofactor, so you might expect variational strategies to be problematic for describing low amplitude wave function tails. And as I mentioned, the probability of sampling the structures at this degenerate point the difficulty is very high. They're very rare events. Takes a lot of hard work to find those guys. So I have a colleague who's a developer of state-of-art quantum mechanical methods. I think of those as the Ferraris of modern theoretical chemistry. I'm driving more the Trabant, so doing empirical and semi-empirical theory, classical MD calculations to treat these systems. So I'd like to focus on the Winkler-Gray experiment for electron transfer, because it is a system where as much as can be controlled in terms of reaction-free energies, activation-free energies, reorganization energies, and their influence on the rate is being controlled. So the Gray-Winkler experiment is this. Take a metalloprotein, maybe a heme protein like cytochrome B562, and modify a surface residue, maybe install a surface histidine or take a native surface histidine and modify it with a ruthenium complex, and trigger electron transfer between one ruthenium complex on the protein surface and the native cofactor for the protein. And by systematically moving those probes, those rutheniated histidine probes around the protein surface, they could probe the influence of distance and protein medium on the electron transfer rate. So we'd like to build models, before we do the quantum chemistry, we'd like to build simple models that make predictions of what they might see in these sorts of experiments. So we can ask, what's the typical decay for tunneling through bond and through space? So we built these models with Jose Onishik in the early 90s, and they go like this. We know from our textbook, our PChem textbooks, the penalty for tunneling drops exponentially as a function of distance, depends on the square root of the binding energy. And so for a 5eV binder, through space penalty for going a particular distance looks like this. We knew as early as the mid to late 1980s, the penalty for tunneling through covalent saturated bonds, carbon-carbon bonds from Gerhard Kloss and John Miller and John Hopfield and Peter Dervin was about a factor of E decay in the wave function amplitude per covalent bond that we tunneled. So Onishik and I decided to try to splice these ideas together to look for what the leading order contribution to the donor-acceptor coupling interaction would look like through an aperiodic medium, a protein medium. And so we said, let's look for the combination of through bond and through space interactions that would maximize this McConnell-like product of amplitude decays. And so what's the leading order contribution, if you like, to the donor-acceptor interaction? And these are the sorts of pathway models that Jose here and I developed with help from our wonderful undergraduate, Joe Betts, who sort of parachuted into our laps. I'll tell you about that in a second, while we were developing these methods. So we know that we knew the covalent bond decay factors through model system data that were emerging in the 80s. Through space decay factors, we could estimate from textbooks. Hydrogen bonds are a sort of combination of bonded and non-bonded interactions. We could splice those together. And the model makes very interesting predictions that actually work. You make predictions, for example, that beta sheets, beta strands are better propagators of wave function tails than alpha helices, just because you go through covalent bonds the whole way and you have a more direct route without through space gaps compared to a helix, compared to a random coil. Hydrogen bonds are good mediators. These ideas were tested by Mike Therian and others. You can propagate very well across hydrogen bond contacts. And through space gaps provide weak links. And these ideas were tested in the Gray-Winkler experiments very well. So we can predict hot and cold spots for electron transfer just based on these models that go one step beyond the square barrier models. Okay. So they look a little bit like the kind of calculation you need to make when you're going through a subway system. So I'd like to get from the southwest of London to the northeast. What combination of tube stops and tube lines should I take? It's exactly the same calculation that we do in the pathway model. It's a graph theory calculation. Instead of having transit distances or transit times, we have v over delta e's. If you wanted to take the logarithm of v over delta e minus logarithm, you'd have an effective transit distance. So it's exactly the shortest distance in a graph problem. It's polynomial in time in computational cost, not bad. So the way we were able to do these early calculations is this fellow Joe. This is a more recent photo of him, but Joe was an undergraduate. He was a sophomore at Harvard, and he called this guy Harry Gray at Caltech and said, Professor Gray, this is Joe Betts at Harvard. I've read all of your papers. I think they're brilliant. I'd like to come to Caltech and work with you this summer. And so Harry, being the sweetest guy on earth, said, of course, Joe, come right out. So Harry set him up in the summer undergraduate research program. At the time, I was working on the technical staff 5 miles away at NASA's Jet Propulsion Lab. And I don't think Harry knew exactly what to do with Joe. He couldn't say no to such a great undergrad. But he called me one day and said, Dave, Joe Betts is coming to Pasadena. You got to do something with him. You got to do something with him. So I said, Harry, send him over. So I was traveling to Brazil to work with Onashik that summer. But we set Joe up with this pathway problem. And he said, Joe, we know you're a great computer programmer. We need to figure out how to get from point A to point B. Here are the rules for tunneling decays. Could you write a program to do this? And we didn't tell him it was a graph theory problem because we probably didn't know it ourselves. But Joe figured it out. I came back after 6 weeks and the problem was solved. So now I always say yes to undergraduate researchers when they ask if they can work with me. Okay, so the interesting aspects I already mentioned, the pathway couplings depend on the protein fold. The simple exponential models are qualitatively right, but quantitatively not so great. We'll talk more about that. There are predicted hot and cold spots for electron transfer. Here's the basic result that came from Joe in these early days. So the square barrier models predict couplings that drop exponentially as a function of distance qualitatively. Hopfield, Yortner, and others were correct. But what we find in the pathway calculations is there's scatter in the pathway couplings by an order of magnitude up or down as a result of the inhomogeneous nature of the tunneling medium. Can be, if they're direct covalent bond pathways, the coupling can be enhanced. If they're not strong pathways, it can be decreased. Okay? And you can make sense of these, so they're simple structure-function relations. As I said, going through a beta strand is more effective than going through an alpha helix, which the helix will mix together through bond and through space contributions. And that translates into an effective decay exponent that would enter the electron transfer rate. Okay? So we're developing these ideas in part motivated by Harry Gray's really seminal experiments on ruthenium-modified proteins that were emerging by the early 80s. And so we knew that if we could make rapid predictions of how the medium influences electron transfer, the Gray group could probably probe these predictions. Calculations capture the right physics, we would argue. They're inexpensive, so we can make predictions faster than anyone could ever test them. And that's the regime we like to be in as theorists. We like to be predictive. So we could already predict that the average exponential decay would be softer in a beta sheet protein like azurin or plasticyanin than it might be in the heme proteins. Gray's group tested that and validated that idea early on. If you want to put that onto other decay scales for tunneling just through vacuum, these, as I mentioned, through bond decay constants are fully half the values that you get for tunneling through empty space. And in other brilliant experiments from the Gray group, they measured the average decay for tunneling through water glasses, which is sort of intermediate between these regimes. Hot and cold spot maps. So I can take my pathway couplings, the strongest pathway, say, from a heme to an amino acid on the protein surface, and I can divide it by the best fit exponential line that I showed you a few slides earlier, and I can identify residues that are privileged from the electronic coupling point of view. Residues that have direct pathways, strong coupling pathways into the heme. Harder to see in this cytochrome structure than here in a plasticyanin structure. So if I'm plugged into beta strands with direct routes into the copper center in plasticyanin, I have anomalously strong, or fast, I should say, electron transfer rates that I predict, and other strands that are not directly plugged into ligands of the copper slow. So this is, these maps contain, I would argue, hundreds of predictions. So we handed off these maps to the Gray group, and they went forth and rutheniated and tested some of these ideas. And so the really compelling data that they were able to generate looked like this here in the case of cytochrome C. So they ruthenium modify at various points on the protein surface. And for example, this is our favorite case, His72. It has a relatively short distance from the heme, but a relatively slow rate, order of magnitude slower than you would expect from its distance. This you can explain by the pathway model because there's a long through-space contact in the strongest pathway that links the heme to the surface amino acid. You can find distances between the heme and the protein surface that are actually further away by 4 angstroms, for example, and the rates will be faster. So the rates out to this His39 residue should be orders of magnitude slower than to His72, but just the reverse is true. And we would argue that that's a result of the structure of the intervening coupling pathways, weak to 72, strong relatively to His39. Right, so it goes one step beyond the square barrier models. There are other tests of these ideas, experiments from Stefan Isiad, the hydrogen-bonded tests I mentioned from Therian. You can explore the tipping point between long transit through bond versus a shorter transit through across a through space gap. So Dave Waldeck, I mentioned earlier, designed systems where he kept his peptidic bridge a fixed length, but changed the shape of the molecule so that in its extended form, the electron will have no choice but to tunnel mediated by the bridge. But if he folds it up into a C-clamp, although there's some through solvent and through space gaps, the electron will prefer to go that way, prefer to tunnel through this gap. And so he can measure those rate differences and probe different mediation mechanisms. So structure really matters. Now, I mentioned how difficult it is to pull out individual electron transfer parameters, and this is why the Gray data is so appealing to us. It's because he set up his experiments to work in a nearly activationless regime where delta G and lambda were approximately matched, and so the claim is that these tunneling timetables reveal the characteristic electron tunneling times for the electron transfer events. And the point I want to make is that the data are scattered. These would be inverses of electron transfer rates. They're scattered by orders of magnitude around the best fit exponential line that would come from a square barrier model. And we can account for these deviations using our pathway model. Okay. Yes, please.
So these are beautiful experiments. It's remarkable to me that there still seems to be arguments about what they mean. I guess what I've always wondered is the extent to which, in looking in biology, at proteins, you can find evidence for or against the idea that nature, productively uses variations in the goodness of the tunneling bridge to control electron transfer in a functional way. Do you have any thoughts on that?
I have two thoughts on that. First thought is the goal of this talk is to present the physical underpinnings of electron tunneling in structured fluctuating matter. So we need to understand that basic physics before we can understand and address the issues of biological evolution and the evolution of electron transfer pathways. The second point I want to make is that nature has at least two exponential knobs to turn in setting electron transfer rates. One is the activation free energy through the Marcus theory or the Arrhenius type ideas, e to the minus activation energy over kBT. That's exponential for sure. And that's the argument in favor of free energy and sort of control of electron transfer in simple distance. The other exponential knob is the tunneling matrix element, and that can be controlled in a coarse sense by distance and in a fine-tuned way by pathways. So the pathway effects that we're describing are order of magnitude, 2 at most, effects, deviations from a single exponential decay line. If you think having an enzymatic reaction rate that's wrong by a factor of 100 is not a big deal, you don't need to think about pathways. But if a factor of 10 to 100 is a big deal for function, then the pathways might matter. Now, I'm not smart enough to address the issue of evolution and pathway evolution and whether biology has recruited it as a tool. We don't know the answers yet. But I think this talk presents the physical underpinnings that may one day let us answer those questions. We have these 2 exponential knobs. This is for sure one of them. Okay.
Is there evidence that proteins have multiple pathways to get an electron?
So it's a great question. So I have a few slides coming up that talk about the few pathway and the multi-pathway regime that we see in these gray group modified proteins. We have not done comprehensive analysis of physiological reactions, physiological electron transfers to ask the few and many pathway questions, but I think that's a great one for the future. So thank you. Okay, other questions? Okay. So this is these are very rich, interesting questions, and there's lots of work for you guys to do. Right? So I haven't even talked about thermal fluctuations. We really need to calculate not just a single squared coupling matrix element, but a thermally averaged one. We can do this now routinely with our pathway methods and with quantum chemical methods, semi-empirical ones at least. And so we analyzed to get to this question about multi-pathways. Tatiana and Igor did beautiful calculations on cytochrome B562, and this addresses the multi-pathway question. They found in some of the derivatives, the cis70 derivative, for example, there was extensive destructive interference. That means the coupling matrix element fluctuated through 0 through this green line as the protein jiggled around. There were other derivatives, like this guy, his73, where the strong pathways were more limited in scope, okay? And so there were the sign changes, this blue line would reflect a sign change, were more rare. So there are few pathway derivatives and multi-pathway derivatives. And so to answer your question, we believe that when the pathways in heme proteins come in through an axial ligand, they tend to be more sparse. So if you want to look for explicit pathway effects, like we saw in that his72 ruthinated cytochrome C, look for derivatives that have pathways coming in through an axial ligand, okay? And so what we've done with the Gray experiments is analyzed the outlying slow rates. And we find that all of the outliers have a weak pathway leading into an axial ligand. And those derivatives that fall better on an exponential line when we pull those guys out have edge-coupled pathways, at least in the heme proteins. And we've analyzed these ideas in more detail. We can talk about whether the mean squared coupling that would feed into our Fermi's golden rule rate is dominated by an average value or a fluctuation away from the average. And I don't have so much time to talk about this. But in those derivatives, let me go back. In those derivatives where we have a relatively sparse set of pathways that provide coupling, then the average value is a perfectly fine metric to use. But in derivatives with multiple pathways, there's a lot of interference among these pathways, and the fluctuation term, here we go, the fluctuation term, the sigma squared term, dominates the mean squared coupling. And so this is maybe more detail than we want to go into. But we can say basically in something like 80% of those modified proteins from the Gray group, fluctuations matter a lot, and you'll find pathway couplings as a result that are characteristic of the secondary structure of the protein. So pathways still matter, even when fluctuations are important. But knowing the appropriate beta value for the secondary structure motif is adequate. So this sort of adds a finer edge to some of the earlier questions about single beta values or not. Other anomalously slow derivatives, I'll go back to the Gray tunneling timetable. Myoglobin His83 has an axial pathway into the heme. His72 I mentioned already a few times, in cytochrome C, an axial path, a through space link. So I think these observations are characteristic of the way proteins wrap around hemes and the nature of sort of the insulation above and below the heme compared to at the heme edge. So we can sort of pull off the anomalously slowly coupled derivatives from these tunneling timetables using these pathway ideas. All right. Okay. So I'd like to argue that we have a semi-quantitative understanding of anomalously fast and slow rates in this Winkler-Gray data by doing the pathway analysis. The anomalously slow guys are all axially coupled. The more average guys, average for their secondary structure, are edge coupled into their heme groups. Okay, so just to summarize, electron tunneling through proteins is a bond-mediated process. The conduits for the tunneling fluctuate. The evolutionary questions are brilliant questions and yet to be fully answered. Statistically, the multi-pathway routes dominate, but the fluctuations do not wash out the underpinning structure in their contributions to the donor-acceptor interaction. Okay, so this is my third folly for the electron transfer discussion, and it links back to your earlier question. So if you're satisfied by making estimates of rates that could be off by 2 or 3 orders of magnitude, a single beta value is perfectly fine. If you want finer resolution, you need to use structured barrier models, whether it's pathway models or quantum chemical models or fancier things. Okay. One other folly that also crops up in the discussion about selection of coupling pathways is, do we measure distances from the edges of cofactors or to the centers of cofactors involved in electron transfer? And I would like to argue that this discussion, well, it's useful because it forces you to explore the extent of localization and delocalization, and this is the right community to experimentally determine the nature of those cofactor localizations. It's largely a moot point, and it's a moot point for the following reason. If I believe that I'm tunneling between 2 edges of my cofactors, there are normalization factors that I should bring into my analysis of the pathway-mediated coupling. And those normalization factors should reflect how delocalized the donor and acceptor states are. This is an idea going back to 74 and Hopfield's original paper on electron transfer theory. So I can tunnel a shorter distance if I go from the edge of my cofactor, but I'll have a normalization prefactor that will diminish the coupling. On the other hand, if I tunnel, say, just to the iron at the middle of my heme, these normalization factors will go to 1, but I'll have to tunnel an extra couple of angstroms. Okay? So you can argue all you like about whether tunneling center to center or edge to edge is relevant, but when it comes to making an estimate of the rate, it really doesn't matter. Some of the parameters in your approximate rate estimates will change, but at the end of the day, your rate estimates will not be very different within the uncertainty of all these simple models. Okay? Okay, so don't get wrapped up in discussions of edge to edge or center to center. It just doesn't matter that much. Going back to the Gray-Winkler data, looking at both the experimental data and the results from extensive structural simulations and coupling estimates, we can say that the standard deviation of the mean squared fluctuations at a given distance compared to the average value of the mean squared coupling at a given distance is larger than 1. So deviations from the mean matter. Okay, so simple square barrier models just don't cut it for us. Okay. What about coupling mediated by water across protein-protein interfaces? Another interesting story, and one that's well worth trying to connect with experimentally. In our modeling, we see that as we push two proteins into contact and begin to pull them apart, there's an interesting plateau region that's predicted in the donor-acceptor coupling, as we get structured water forming at the protein-protein interface. And then as we pull the proteins apart further and the water becomes more disorganized, we get tunneling that would be characteristic of the bulk water number. So folks have been looking for these sorts of plateau effects associated with structured water at protein-protein interfaces, still an open issue. Okay, so I'd like to take the last 5 minutes and just make a connection with DNA electron transfer, a very interesting, physiologically relevant electron transfer problem, and one that highlights the differences in the coupling regimes at play for us. Okay, so there have been basically 2 generations of DNA electron transfer experiments. One in the early 1990s, brilliant experiments, very complex experiments. The structures were perhaps a bit fragile. Distances were not so well characterized, many experimental complexities. And a second generation that followed where a hole was injected into the DNA and that hole was watched as it propagated from place to place. We're going to focus on the second set of DNA electron transfer experiments. You can read the popular literature. The headlines were phenomenal. I knew that the field was in an interesting state when this fellow, Mr. Talbies, who wrote a book on cold fusion, called me one day and asked me to comment on DNA electron transfer. But with the advent of improved experimental designs, I think many of the fundamental mechanistic issues are being resolved now. So with respect to energetics, the energetics of the bases, the oxidation potentials of the bases look more or less like this. So purines are more readily oxidized than pyrimidines. So this creates the energy landscape. So rather than having, for example, a 2-electron volt barrier for electron transfer, if I oxidize a G and watch the hole move, say, through an AT chain, the barrier for tunneling is on the scale of tenths of electron volts, not electron volts. So you'll see plots that look like this in the literature from various excellent groups. Rapid decay of electron transfer rates at short distances over a couple of base pairs, and then slower decay at longer distances. The basic party line is that at shorter distances, the electrons are tunneling. At longer distances, they're hopping incoherently, doing multi-step hopping, just like in our electron transfer proteins. You can rationalize this by plugging in a 2 eV barrier height for square barrier tunneling and calculating Boltzmann populations for 0.2 of an eV barriers. And you'll find that at about 3 or 4 base pairs, the tunneling propensity and the thermal populations will more or less match. Okay? We've thought about this a lot. It's not a bad starting point. But if you think about those Marcus theory, vibronic couplings and non-equilibrium broadenings, vibronic broadenings of the electronic states, they are also on the scale of tenths of eV. So if I go back to my energy level diagram, the non-equilibrium fluctuations of the medium will move these G's and A's into resonance transiently all the time. So we were interested in whether we could see that. Here's some calculations of molecular orbitals for DNA. This is what the orbitals look like most of the time. The frontier orbitals are G localized in this GTAC short strand. But if you do geometry sampling, you'll find that sometimes the A's fluctuate, and you find frontier orbitals that are A localized. So this would correspond to a structure with a non-equilibrium fluctuation where the hole would rather be on this intervening A than on a terminal G. Okay? So this led us to ask questions about what the mechanism of electron transfer might be in the regime where the energy gap between orbitals, the non-equilibrium polarization fluctuations, and the coupling matrix elements are all about the same. So the coupling between stacked bases in DNA can be as large as 1/10 of an electron volt, 0.1 eV. The energy fluctuations I mentioned all along are on the scale of tenths of eV, if lambda is about 1, and kBT is 25 millivolts. And delta E's, we said, are also on the scale of tenths of eV for DNA bases. Okay, so what's the theory going to look like? Well, there's an interesting regime. You could have tunneling at short distance. That's a legitimate mechanism. But you could also have the following. You have these vibronically broadened levels. You could have a transient matching of those levels, a sort of transient resonant mechanism for electron transfer. And the amusing thing about a mechanism like this is it would also decay exponentially with distance. Although it looks resonant-like, the probability of matching many things, if each has a probability less than 1, is multiplicative. So if I multiply many things together, the net probability of matching those many things will drop exponentially with the number of things I'm trying to match. So I'll get resonant transport that could masquerade as tunneling transport just by virtue of the exponential decay characteristic for the rate. So we developed a theory with our collaborators and students here. It was published a couple of years ago that makes an estimate of what the tunneling decay would be in systems like this. So I would add as the sort of final folly is that in short systems where those fluctuation parameters, gaps, and couplings are all on the same order of magnitude, that the idea of a pure tunneling mechanism at short distance is probably not quite right. There will be a tunneling contribution, but it may not rule the day. So we call this new mechanism transient or flickering resonance. It can produce exponential distance dependence for ET rates without invoking any tunneling mechanism at all. The physics of DNA that can support these sorts of mechanisms is that the bases nearby are in similar environments, similar aqueous environments, and feel similar polarization fluctuations. So if the polarization fluctuations are correlated, that reinforces these flickering resonance mechanisms further. Okay, so I don't have time to speak about it, but the characteristic tunneling, transport decay length has nothing to do with tunneling now in this flickering resonance model. It depends on the magnitude of the vibronic broadening, the broadening of the coupling matrix elements around 0, and amusingly, this effective decay constant for flickering resonance is on the same scale as is seen in experiments measuring the distance dependence of DNA electron transfer. So we've proposed this as a possible mechanism. It will have different temperature dependence from traditional electron tunneling in biomolecules, and so we're trying to engage some of our experimental friends in probing whether this flickering resonance mechanism may be operative in these low barrier, strongly coupled biosystems. Okay, so let me stop there. So I think that probably Mr. Longet-Higgins was too narrow in his thinking about the role of quantum mechanics in biology. We're tunneling electrons in bioenergetics, so we have to think about quantum mechanics, no escaping the dual nature of the electron. I think Mr. Kaufman may be pushing a little too hard on this, but we'll see. It's the century of neurobiology, so wouldn't it be fascinating if he were right? I think he's a little too cynical, although I love him. And Feynman, who can argue with Feynman? Yeah. So I'll just end by thanking you and thanking my more senior collaborators. I apologize for not being able to mention all of the students who were involved, but you saw their names going by on the individual slides. My senior theoretical collaborators, Jose Onishik in the early days on the pathway models, and more recently on flickering resonance, DNA electron transfer, and many other wonderful projects, Spiros Skortis at the University of Cyprus. And in the posted file, you'll see some references to historic papers and textbooks. Some of the papers that describe details of what I spoke about today and our most recent work. And for those of you who are really interested in details, I posted a couple of exercises. We sometimes teach an electron transfer course, so you can look at those at your leisure. And I thank you once again and be happy to answer any more questions.
Thanks, David. Are there any questions?
So I just have one question about the work you did on the pathways for the electron transfer. So those secondary structures, they're not symmetric in space. So how do you, have you observed any difference, like if this is alpha helix going this way or the other way, or beta sheet?
Yeah, that's it's a great question. So we don't see asymmetry in the coupling matrix element at all. There are experiments from Marianne Fox from some time ago, a couple decades ago, where she measured electron transfer through model alpha helices, so synthetic helices, with their intrinsic dipole moment, with donor and acceptor this way and reversed. And she interpreted her data as being explained. Rates were different when she reversed the donor acceptor positions. She interpreted her rate difference as arising from the influence of the helix dipole on the reaction free energy. So the sort of activation free energy effect, the Marcus theory, activation free energy, delta G plus lambda, quantity squared over 4 lambda. So there are those sorts of effects, but if you wanted to take it further, you could ask, how does the helix dipole, how does it influence the shape of the tunneling barrier? Now, the simple pathway arguments, square barrier arguments, have embedded in them the idea that those effects are screened out. Now, I think it remains an interesting question as to whether those helix dipole effects could have a qualitative influence on the tunneling interactions or not.
All right, thank you.
Nature has evolved in some proteins this mechanism by which electron transfer is gated by substrate binding. What's happening here? Is it that the donor and acceptor energy levels are becoming equalized, or is it the change in geometry that's responsible?
Right, so that's really a fabulous question. We're actually working on that very question in collaboration with Judith Klinman at Berkeley in copper monooxygenases, where there are 2 copper centers, one catalytic and one a sort of electron reservoir, and we'd like to know how the electron transfer is aware enough to deliver, the electron transfer mechanism is aware enough to deliver the electron to the catalytic center at the right time in the catalytic process. So the qualitative answer I would give now is that you have 3 control points in electron transfer: reaction-free energy, reorganization energy, and coupling matrix element. So if you cause a switching in any of those parameters, you could get an order of magnitude change in the electron transfer rate. So substrate binding, could obviously change the free energy for the electron transfer reaction. That might be the first place I would look, for example. But if substrate binding causes conformational changes, that could alter the electron transfer distance or the coupling pathways. Distance changes, exposure to solvent, that could change lambda. So I think this is a really rich area for investigation, and I think the jury is still out. It probably depends on the specific catalytic process.
Are there any other questions? See, there is one over there.
Hi. My question is, I think in some reactions where there are two electrons, net electrons transferred, in such cases, how do I know like the two electrons are transferred one by one or somewhat coherently?
Yeah, so that's a great question. So if you're interested in a somewhat speculative technical analysis of this question, we just wrote a paper in the last year where we calculated two electron transfer coupling interactions, assuming pure coherent transport. So this is a very interesting, long-standing question. So if I have two electrons that I'm going to move, and I move them coherently, move them at the same time, the effective barrier for moving them might be twice as large as what we spoke about today. So the tunneling barrier should be larger than if I move them one by one. But there are other issues, there are other elements of the coupling story that could be stronger. So there's a kind of explosion in the number of pathways because I'm moving two particles in a virtual sense through the bridge. So there can be combinatorial factors that could make the multi-particle tunneling stronger than you might otherwise expect. So I think this is a totally open issue. I think most people would guess the propensity would be to move the electrons one at a time. Both lambda and lambda would be larger for two charges as opposed to one, and the tunneling factor would tend to be less favorable. So the sort of party line would be less favorable to tunnel two particles rather than one. But I think it remains open. And if you look at our paper, you can see we were trying to make guesses about what circumstances would favor moving multiple particles. If you have unusually large driving forces, for example, since the activation free energy comes from a matching between lambda and delta G, maybe at exceptionally large driving forces, this larger lambda value could be accommodated better than for moving a single electron. So there may be special circumstances where you could move them coherently. I think it's an open question.
Are there any other questions?
How do you consider the difference in oxidation state between two electron transfer relays? For example, the heme you talked about and the water network in between the proteins. When we happen to oxidize or reduce one of the relays, how does that affect the electron transfer rate?
Let me try to restate the question and make sure I understand it. I think this is a great question. The question is, how does the redox state of the cofactors, how do the redox states of the cofactors themselves, or may they structure the intervening medium? That's a very interesting question. So I don't have a good general answer for you. This is something that could be probed in simulation. So you might imagine that and it connects with the earlier question about synchronization of electron transfer events. You could imagine that when a redox protein rearranges into a particular state, it might favor, say, the delivery of the next electron from a particular site. So this could be studied. This could be studied experimentally. The closest we've come to this is studying electron delivery and nitrogenase from the smaller 4-iron 4-sulfur protein to the molybdenum-containing protein, and that's ATP coupled. In that case, we've seen evidence for ATP binding and conformational change as setting up strong electron transfer pathways. But that's probably the closest we've come to addressing your question. Yours is a more subtle one, just about redox state causing pathway structuring. Very interesting question. The potential, yes. So any rearrangement of the kind you talked about could also shift redox potentials. There's a group actually, now that I think about it, I believe there's a PNAS paper from a group in Argentina that has thought about these issues to some extent. I'd have to dredge up the name of that group, but if you email me, I could find that.
All right. Well, if there are no further questions, let's thank
Thank you. Thanks very much.